Assalamu alaikum. Good afternoon, ladies and gentlemen. It is my pleasure to welcome you to our presentation, Supervised Machine Learning Approaches for Log-Based Anomaly Detection, a case study on the Spirit dataset, conducted within the Labri SPA laboratory at the École Supérieure d'Informatique of Sidi Bel Abbas, Algeria. My name is Mohamed Bakouche. I will present our research on anomaly detection in system logs, an important task for ensuring reliability and security in modern computing systems. We are honored to present these findings at the TAC 2025 conference, and we look forward to fruitful discussions. Thank you, and let's get started. In this presentation, I will start with the introduction. I will then move to the related work, reviewing existing approaches. After that, I will present the Spirit dataset, highlighting its main characteristics and how it was prepared for our experiments. The next part is the methodology, where I will explain the feature extraction techniques, the supervised models we used, and our evaluation strategy. We will then examine the results and analysis. Finally, I will end with the conclusion and propose future research directions. Introduction. Anomaly detection is essential for building secure and reliable computer systems. As modern systems grow more complex, they become more prone to bugs and vulnerabilities that attackers can exploit. Even minor issues may cause user dissatisfaction or significant financial losses. Traditional data mining techniques are no longer sufficient to address these challenges. Modern systems continuously generate massive volumes of log data, which are critical for system monitoring, diagnosis, and maintenance. Logs record events and internal states during system execution, providing valuable insights into system behavior. Log-based anomaly detection aims to identify abnormal system behaviors, potential early indicators of failures, by analyzing the log data produced during system execution. While developers can manually inspect logs to detect anomalies, the volume and complexity of logs in modern systems make manual inspection extremely challenging, if not infeasible. Machine learning approaches provide effective solutions by automating anomaly detection and enhancing detection accuracy. Machine learning has become central to log-based anomaly detection, enabling the automated identification of abnormal behavior from large-scale system logs. Unsupervised approaches are commonly used when labeled data is unavailable, but they are prone to false positives since they rely only on unusual patterns. In contrast, supervised methods achieve high accuracy when labeled data is available, as they learn directly from examples of normal and abnormal behavior. The Spirit dataset generated by the Spirit supercomputing system at the Sandia National Laboratories contains millions of log messages with verified anomaly labels. Despite its potential, it has been little explored in supervised anomaly detection studies. These datasets provide a valuable opportunity to evaluate the effectiveness of such models. In this work, we assess four supervised models, SVM, decision tree, random forest, and XGBoost, using two feature extraction techniques, TF-IDF and word2vec, and five time-based fixed windows. Results show that shorter windows significantly improve performance. Tree-based models, decision tree and XGBoost combined with TF-IDF achieve the best results, while SVM performs strongly with word2vec. These findings confirm the importance of both feature representation and temporal segmentation in anomaly detection. In the field of log-based anomaly detection, researchers have developed a variety of approaches which can broadly be grouped into supervised, unsupervised, and semi-supervised methods. Supervised methods rely on labeled data and typically use classification algorithms to distinguish normal and abnormal behavior. These techniques commonly achieve high accuracy when quality labels are available, but they are limited by the cost and difficulty of labeling large datasets. Unsupervised methods, on the other hand, operate without labels and assume anomalies are rare and different from normal patterns. Techniques range from statistical analysis and clustering to advanced deep learning models which learn system behavior and flag irregularities. While widely used, these methods are more prone to false positives. Semi-supervised methods attempt to bridge the gap by leveraging a small amount of labeled data to support learning, thereby improving detection performance in scenarios where labels are scarce. Most existing studies rely on popular datasets such as HDFS or Thunderbird, while the speed dataset remains unexplored, especially in supervised settings. In this work, we aim to investigate it further to assess the effectiveness of traditional supervised machine learning models for anomaly detection. The Spirit, the Spirit dataset. The Spirit dataset contains log data from the Spirit supercomputing system consisting of over 172 million messages labeled as normal or anomalous. For efficiency, we use a 1 gigabyte subset with 5 million entries, of which about 15.3 are anomalies. In our experiments, log sequences are generated using fixed time based windowing strategy with window sizes of 1, 5, 15, 30 minutes, and 1 hour. A sequence is labeled anomalous if it contains at least one abnormal log message. The resulting datasets are split into training 80% and testing 20%, ensuring a balanced distribution of normal and anomalous sequences. This table summarizes the main characteristics, including the number of sequences, anomalies, and anomaly ratios for each version. Methodology. The log-based anomaly detection framework main steps are log parsing, feature extraction, and anomaly detection. These steps are illustrated in this figure. The purpose of log parsing is to transform unstructured log messages to structured formats by extracting event templates. The objective is to separate variable components from the constant structure and generate standardized event templates for each log message. This transformation is commonly performed using automated log parsers such as Drain and Spell. This slide illustrates an example of log template generated from a raw log message from the Spirit dataset. Here, all variable parameters are replaced with the token star. In our case, we use a pre-parsed version of the Spirit dataset. Each log entry in this dataset includes structured files such as the timestamp, event ID, event template, and anomaly label, which serve as input for the subsequent processing steps. The feature engineering step encodes raw logs into numerical feature vectors for machine learning models. To achieve this, log entries are first grouped into sequences. Because the Spirit dataset does not provide explicit identifiers such as session IDs, we rely on timestamp-based grouping. Two common strategies are fixed and sliding windows. Both use chronological ordering of events to capture temporal patterns in system behavior. In our study, we use the fixed window strategy, which divides logs into distinct groups according to predefined time intervals. The procedure used to segment log entries into sequences using a fixed time window is illustrated in this algorithm. This method relies on a specified time interval to split the chronologically sorted logs into distinct sequences. For our experiment on the Spirit dataset, we generate 5 versions of log sequences using time window sizes of 1 hour, 30 minutes, 15 minutes, 5 minutes, and 1 minute. As the window size decreases, the number of generated log sequences increases, while the average length of each sequence, i.e., the number of log entries it contains, decreases. The algorithm assigns a label to each sequence based on the presence of abnormal log entries. A sequence is labeled as abnormal if it contains at least one abnormal log entry. Otherwise, it is labeled as normal. Each sequence can be represented using either event IDs or event templates. The choice depends on the method used after to extract variable features from log sequences. In this study, we use two popular techniques, TF-IDF and word2vec. For TF-IDF, the sequences are represented using event IDs, while for word2vec, the sequences are represented using the actual event templates. TF-IDF term frequency inverse document frequency measures how important an event ID is within a given sequence compared to its importance across all other sequences. Each log sequence is transformed into a sparse vector, mostly zeros, of size equal to the total number of unique events in the dataset, 2880 in our case. For each sequence Sj and each event ID Ei, we compute the corresponding TF-IDF value using the following formula. The formula is shown in this slide. In this formula, n denotes the total number of log sequences. Big N denotes the total number of log sequences. Small n represents the number of sequences in which the event ID Ei appears. In contrast, Word2Vec learns a dense vector embedding for each log template based on its surrounding context, i.e., neighboring events in sequences. It captures semantic similarities between log events. In our study, we train a Word2Vec model on the entire set of log sequences, treating each event template as a word in a sentence. The model learns a fixed size vector representation for each event template. We use a 500-dimensional vector in our case, such that events that commonly appear in similar contexts have similar vector representations. Based on the labeled future vectors constructed in the previous step, we train supervised machine learning models to distinguish between normal and anomalous log sequences. The trained model can then be used to predict labels for new and seen log sequences. In our study, we use four models: Super Vector Machine or SVM, Decision Tree, Random Forest, and XGBoost. To evaluate the performance of each model, we split the log sequences of each spirit dataset generated using different fixed time windows into training and test sets using an 80% training ratio. We applied a uniform split strategy to ensure that the proportion of anomalous log sequences is consistent across both sets. Each model is trained on the training data and then evaluated on the test data. After testing, we compute standard evaluation metrics, precision, recall, and F1 score. We compare the performance of the models across two feature extraction techniques, TF-IDF and Word2Vec, and across different versions of the dataset created using various time window sizes. Results and analysis. This table presents a comparison of the performance of the four supervised learning models used in our study: SVM, Decision Tree, Random Forest, and XGBoost. The evaluation is conducted across 5 fixed time window settings: 1 hour, 30 minutes, 15 minutes, 5 minutes, and 1 minute, and two future extraction techniques, TF-IDF and Word2Vec. The models are assessed using three standard evaluation metrics: precision, recall, and F1 score. All models exhibit a noticeable improvement in recall and F1 score as the time window becomes shorter. This can be attributed to the fact that smaller windows produce a larger number of log sequences, each containing fewer events. This facilitates better isolation of anomalous patterns and reduce noise within individual sequences, making anomalies more distinguishable. This figure illustrates the trend in F1 score for each model as the time window decreases. The results highlight the benefit of grouping logs using shorter time intervals. This approach increases the number of sequences while simultaneously enhancing the ability to capture subtle and specific anomalous behaviors. SVM shows moderate performance across all settings. Its results improve notably with shorter time windows using Word2Vec, reaching an F1 score of 0.966 at the 1 minute window. These results suggest that SVM benefits more from dense semantic word-to-vec embeddings than from sparse TF-IDF representations. Decision tree. Decision tree model performs strongly at short time windows, particularly with TF-IDF futures. It achieves a perfect precision in civilian configurations, including TF-IDF at, at 5 minutes and 1 minute windows. Its best F1 score of 0.973 is obtained with TF-IDF at 1 minute. Random forest provides consistently strong results across all window lengths and feature types. It reaches its highest F1 score of 0.947 with word2vec at 1 minute. XGBoost. XGBoost performs competitively, particularly in shorter windows settings. It, like decision tree, it achieves an F1 score of 0.973 with TF-IDF at 1 minute. Regarding future extraction, TF-IDF shows better results with tree-based models, decision tree, random forest, and XGBoost, especially at shorter windows. Word2vec is more effective with SVM, highlighting the benefits of dense context-aware embeddings for linear classifiers. These two slides present the results analysis already explained directly on the table. Conclusion. In this study, we presented a comparative evaluation of 4 supervised machine learning models: SVM, decision tree, random forest, and XGBoost. These models were applied to the spirit log dataset using TF-IDF and word2vec for future extraction. By applying a time-based fixed window grouping strategy with varying window sizes, we assessed how log segmentation affects anomaly detection performance. The experimental results indicate that reducing the time window significantly improved detection accuracy across all models. The 1 minute window produced the highest F1 score, confirming the benefit of finer log segmentation. Decision tree and XGBoost, particularly when used with TF-IDF, achieved the most accurate results, both reaching an F1 score of 0.973. SVM also performed competitively with word2vec at shorter time windows, achieving an F1 score of 0.966. These findings highlight the effectiveness of tree-based supervised models combined with structured feature representations. They also confirm that adjusting log grouping parameters can greatly enhance anomaly detection capabilities. As future work, we plan to investigate ensemble techniques such as voting among decision tree, random forest, and XGBoost, explore hybrid features that combine TF-IDF and word2vec, and apply explainable AI methods to better interpret model decisions and anomaly attributions. Thank you very much. Questions are welcome.